Hello students, very good afternoon. My name is Ravi Ranjan Kumar and I welcome you to this session. This week we are revising heat and thermodynamics. This is the last lecture of this series. Today we will try to cover first law of thermodynamics. Although it is not possible to do justice to this chapter of a first law of thermodynamics, but I will try my level best. Okay, so without losing any further time, let's share our screen. So here we go. So first law of thermodynamics is nothing but a form of work energy theorem. Okay. So when a closed system undergoes a thermodynamic process, let's say from state P1, V1, T1 to another state P2, V2 and T2, you must assume that these states are equilibrium states. So let's say this is initial equilibrium state and say this is final equilibrium state. Okay, so when this thermodynamic process undergoes, okay, so there is some exchange of heat, there is some change in internal energy, and there is some work done by the system. Okay, so these quantities are related. Say for example, if delta Q amount of heat is supplied to the gas, okay, it will be either stored in form of internal energy, so internal energy will be increasing, and the another part would be nothing but the work done by the gas. So it is clear. Let's also notice the sign convention which we use in physics. So delta Q, which we are writing over here, is nothing but heat given to the system. Heat given to the system. Okay. And delta U is nothing but the change in internal energy of system. Okay, and we discussed about internal energy in kinetic theory of gases. We will be using the same definition of internal energy here as well. And this delta W, according to the sign convention which we use in physics, is nothing but the work done by the gas. Done by the gas. Please notice. Okay, and that is something different which you use in chemistry. Okay, so this is first law of thermodynamics, and that is valid for a closed system. That is valid for a closed system. That means there is no exchange of mass between system and surrounding. Okay, so this is first law of thermodynamics. As you see, this is nothing but the work energy theorem over here. Alternatively, you can write delta W is equal to delta Q minus delta U. Okay, and in differential form, this law can be stated as, for example, dq is equal to du plus dw. dq is the infinitesimal heat added to the system, du is the infinitesimal change in potential energy, and dw is small work done by the gas over here. Okay, so let's try to understand each and every term in this first law of thermodynamics. What would be work done by the gas? What would be the change in internal energy? And hence, what would be the heat added to the system? Delta Q. Can we find that out? So let's start our discussion from the work done by the gas. Work done by the gas. So let's try to model a simple picture. So let's say we have a cylindrical container, okay, which has a movable frictionless piston, let's say, and some gas is enclosed in this cylinder over here. Let's say cylinder cross-sectional area A is uniform, okay, and this is the piston over here. So let's say the state of gas we are defining, let's say at this instant its pressure is P and the volume occupied by this gas is V. So this for by the system of gas, this gas will be doing some work over here, because you realize that due to this pressure, okay, the gas will exert some force on this piston, okay, and that force would be nothing but pressure times area. And due to this force, okay, the piston will move infinitesimal distance, let's say dx. Okay, so in that case, work done by the gas, that would be simply nothing but equal to force dot displacement. So that is going to be P times A times dx. And you should notice that A dx is nothing but the volume, change in volume of the gas. So you can also write it as P dV. So that is the small work done by the gas when the displacement is small or the change in volume is small. So total work done from some initial state to final state, we can find out, or delta W, let's say. So P dV, that would be some integration from some initial state to final state. And you should also realize that this term over here, geometrically speaking, this is nothing but area under curve of P versus P graph. So in physics, this is the most important graph, P versus V, because it enables us to find out the work done by the gas. And the physicist is most often interested in work done by the gas. How much work can he extract from the system? So this is the most important graph, P versus V graph over here. And the meaning of this thing is the area under curve. When we are saying is the work done by the gas, what we mean is simply this. For example, this is P versus V plot, and say this is some state 1 and this is another state 2, and gas is undergoing a thermodynamic change from state 1 to state 2. So there can be infinite processes connecting these two states. Like it could be either this, it could be either this, some and any type of process is possible. So let's say, for example, through this path, the gas is undergoing a thermodynamic change from state 1 to state 2. So what we can say over here, the work done by the gas would be simply the area under curve. Let's say here, well, volume is V1 and volume is V2 over here. So area under curve of this process or this curve over here will be simply this. So this is nothing but the work done by the gas, delta W in this case. And you should also realize a few points, like for example, work done by the gas will be path dependent. That is, it will depend upon the path taken by the gas or the process. For example, if we would have gone through this path, the work done would have been something else. If we are going through the work through this path, the work done, the area under curve is something else. That is quite visible from this diagram over here. And the another thing you must understand, that delta W will be positive for expansion of gas. For expansion of gas, that is increase in volume, you can say increase in volume. Okay, expansion we are saying for increase in volume. And delta W would be negative, means work will be done on the gas. So work done by the gas, you can say that would be negative, and that would be for compression. Okay. Okay, that is for decrease in volume. So these are two important points you should understand about work done by the gas. Okay, so two important processes, let's look at it and how what would be the work done by the gas in those processes. The one process, let's me take, is isobaric process. Isobaric process simply means like pressure is going to be constant, and if it is following ideal gas law, okay, so then V by T would be constant as well. Okay, so V is directly proportional to T, you can say. So when you will be looking at its pressure versus volume graph, P versus V graph, so you should realize the pressure is constant over here. Okay, so from state 1 to state 2, like when we are going, the pressure remains constant, and let's say volume is changing from V1 to V2. So finding out work done in this case is really easy. And this would be this area, which is nothing but that of a rectangle. And that would be simply P times V2 minus V1, or simply you can write P times delta V. Or you can also write like P V2 is nothing but nRT2, and P V1 is nothing but nRT1. So you can also write it as nRT2 minus T1, or simply nR delta T. So for an isobaric process, the work done by the gas will be given by this expression. Similarly, let's look for another important process, that is isochoric process. And isochoric process simply means that the volume is going to remain constant for a thermodynamic change. So that means like P by T would be a constant, or P would be directly proportional to T. And when you will be looking at P versus V graph for an isochoric process, for a constant volume change, let's say from state 1 to state 2, you can see that the volume here is constant. Only the pressure is changing from, let's say, some P1 to P2. And you can clearly realize that this curve, the area under curve, is simply equal to 0. So that is a very, very important result, that work done by the gas for a isochoric process is equal to simply 0. Okay, so this is a few things about work done by gas, which obviously we will be talking more, okay, in the coming discussion. Okay, so before moving on to the discussion of change in internal energy, okay, let's try to understand one important parameter, that would be molar specific heat capacity of gas. Okay, let's say C, small c, let's say. So small c, that is defined as heat required by the gas to change the temperature by 1 unit per mole. So C is nothing but dq by n dt. That is how it is defined. And we define two other important quantities, let's say for example CV and CP. This V and P, these are the subscripts over here, which stands for constant volume and constant pressure respectively. So CV is nothing but molar specific heat capacity of gas at constant volume process. And the another one is molar specific heat capacity of gas at constant pressure. Okay, and now my objective is to find out a relationship between CP and CV. So let's try to find that out. So let's say we are willing like to have the same temperature change. Okay, first in case of isochoric process, and then we want to have it in a case of isobaric process. So let's say for same rise in temperature, for example let's say dt. Okay, so for at constant volume, or you can say isochoric process, you can say this equation would be how much heat would be required, let's say dqv. So the according to the first law of thermodynamics, this is going to be du plus dw over here. And dw, as we know, that this term is nothing but equal to 0. So you should realize that dqv is equal to du, and according to the definition of cv, dqv, we can simply write it as ncv dt, and that would be the value of du. So let's say that is equation number 1. Okay, and at constant pressure, dq p, let's say, that would be equal to, again according to first law of thermodynamics, that would be du plus dw over here. And let me tell you, according to our definition of cp, dqp can be written as n Cp dt, where change in temperature I have taken same in both the cases, so this would be dt. And you must understand, like, change in internal energy is a quantity which is going to depend only upon change in temperature. So for constant volume process or constant pressure process or whatever the process is, the expression for du is going to be same. So that again would be nothing but ncv dt. And dw, for a constant pressure uh, uh, process, we learned that it would be written as nr dt over here. So simply you can see that n both side n dt will get cancelled, and you will be getting cp is equal to cv plus r. So that gives us cp minus cv is equal to basically r. Okay, so that's the idea. Okay, so also we know from kinetic, so that is a very, very important equation. Let's say, let's circle it. And also we know from kinetic theory of gases that internal energy, like for a gas, for an ideal gas, will be having only the total kinetic energy of the gas, and there would be no interaction between the molecules. So potential interaction energy or potential energy of the gas will be equal to 0. And we learned that it would be nothing but n times f r by 2. Okay, so f is nothing but degree of freedom, and r by 2, from the law of equipartition of energy, we said that for each degree of freedom, r by 2 energy would be associated per mole. Okay, and that multiplied with t, that was nothing but the potential internal energy over here, where f is the degree of freedom. That could be translational and rotational, and we are not talking about any vibrational degree of freedom over here, because we will be limiting ourselves to the discussion at low temperatures only. So delta u, we can simply write it as n fr by 2 into delta t. And comparing this equation from the above equation which we got for delta u is equal to ncv delta t, you should realize that cv would be nothing but fr by 2 over here. So that you should realize. So once we have realized that, and also, like, f, you must understand that is nothing but f translational plus f rotational. Translational degree of freedom for a monoatomic gas or polyatomic gas or whatever type of gases, it will be 3 always, and rotational degree of freedom will be 0 for monoatomic gas, and that would be 2 for a diatomic gas, and that can be 3 for a polyatomic gas which is non-linear. So once we know these quantities, like for different types of gas, we can draw a table over here. Let's say 3 type of gases we will be looking at. So that is, first is monoatomic, the second one is, say, diatomic, and the third one is, say, polyatomic. Okay, so let's first column, let's write the degrees of freedom of each. So monoatomic will be having 3 translational degree of freedom only, and here for diatomic 3 translational plus 2 rotational over here. So total degrees of freedom would be 5. And for polyatomic over here, and let's specify that should be non-linear. Okay, for example, if it is linear, it will only be having 2 rotational degree of freedom, but for non-linear, that would be 3 translational plus 3 rotational as well. So total will be 6 over here. So this is the column for degree of freedom. From this column we can derive another column, that is cv. Okay, molar specific heat capacity at constant volume, and this expression is nothing but fr by 2. So this gives us 3r by 2, 5r by 2, and that would be simply 3r. And then we can derive a column for cp, because cp is nothing but cv plus r we have just derived. So this would be nothing but 5r by 2 and 7r by 2 and 3r plus r, that would be 4r. And let's also derive one more column, that would be adiabatic exponent of gas, and that is defined as the ratio of cp and cv. In this case, that would be cp we have got and cv we have got, we just have to divide. So that gonna be 5 by 3, and that would be 7 by 5, and that would be 4 by 3. Okay, so this table is very, very important, and please understand this table is for ideal gas, that is low density gas, or you can say we are operating at low temperature over here. Okay, and also two important relationship, like since we know that Cp minus Cv is equal to R, and Cp by Cv we are saying it to be gamma, and from these two equation Cv we can write it as R upon gamma minus 1, and Cp we can write as gamma times R upon gamma minus 1. So this is the thing. So being said that, now we can write the expression for change in internal energy. Change in internal energy. Okay. Delta U expression would be now given by NCV delta T, and for different types of gases now we are able to get like what is the value of CV, and also from this equation please understand that would be nothing but NR delta T upon gamma minus 1. Please understand that. Okay, so you should realize that internal energy is a purely state function, that is it will its change in internal energy will only depend upon initial and final state of thermodynamic process, and it will not depend upon the process, it will not depend upon the path. So that is very, very important property of change in internal energy. So now the next thing for us to discuss is, let's discuss about isothermal process. Isothermal thermodynamic process is simply a process in which temperature is going to remain same throughout the process. So that means PV would be a constant. As I said, that P versus V graph is most important for the physicist. So here P versus V graph will be a rectangular hyperbola. So this will be looking at like this. So this is, let's say, some temperature T1, okay, and at some other temperature T2. So this would be something like this, for other temperature something like this. So you should realize that T3 is greater than T2 is greater than T1, and all these curves are known as isothermal curves, okay, which are drawn at different temperatures, you should realize. Okay, um, so also you should notice like slope of PV curve for isothermal process. Okay, so like you understand that PV is equal to constant, and if you differentiate both sides, so you will be getting P dV plus V dP is equal to 0. So this clearly gives you the slope of P versus V graph, that is dP by dV, that will be equal to minus P by V over here. So that is one important thing. And another thing we are looking for over here, to apply first law of thermodynamics for an isothermal process. So you should realize that temperature is not changing. So clearly the change in internal energy will be equal to 0 for any thermodynamic process which is isothermal. And work done by the gas, delta W, one formula we have already got for work done by the gas, that is nothing but P dV integral from initial to final state. And for an isothermal process, P we can write it as nRT by V. So nRT V dV, nRT by V dV from initial to final, and you should realize this term is constant, so this will be coming out. So nRT, that is at constant temperature, and this will give you ln, say, V2 by V1, or alternatively you can write it as nRT ln P1 by P2, because P1 V1 is equal to P2 V2. Okay, so this would be the work done by the gas, and obviously according to the first law of thermodynamics, since delta U is equal to 0, delta Q will be simply equal to delta W over here. So that is one another thing. One another thing I want you to notice is the molar specific heat capacity for the gas in isothermal process. So C, which is defined as dq by n dt, and you should realize dt is 0 over here. So molar specific heat capacity for isothermal process will be tending to infinity, you should realize. So that means no matter how much heat you are giving to the gas isothermally, okay, its temperature will not rise because temperature is constant over here. So that is for the isothermal process. Now let's look at another important process, and that is adiabatic process. Adiabatic process is the process in which in every small step the heat exchange between system and surrounding, let's say dq, is equal to 0. So that is how adiabatic process is defined. Okay, so please understand, delta q is equal to 0 does not ensure that the process is adiabatic. So at every step dq should be equal to 0 over here. Okay, so if dq is equal to 0, according to the first law of thermodynamics, you can write du plus dw is equal to 0. Okay, and du we have learned how to write that. Like du we can write it as nr dt upon gamma minus 1, and dw you understand is nothing but p dv, that will be equal to 0. So nr dt we can write it as um, nRDT. From ideal gas equations, you understand that PV is equal to nRT. So if we differentiate both sides, so PdV plus VdP will be nothing but nRDT. So at this place, let's substitute that value. So we will be getting PdV plus VdP upon gamma minus 1 plus PdV is equal to 0. So this is a differential equation in P and V. So when you will be rearranging that, you will be getting gamma P dV plus V dP is equal to 0. And let's separate the variables. So dP by P will be equal to minus gamma dV by V, and let's integrate both sides. Okay, so what you will be getting over here is nothing but ln P plus gamma ln v is equal to some constant, and you can rearrange it to give pv to the power gamma is equal to constant over here. So for an adiabatic process, okay, the pressure and volume will be related by this expression, pv to the power gamma is equal to constant. And looking at this also, like you should also realize, like the slope of an adiabatic curve dp by dv, you should realize, is nothing but minus gamma p by v. Okay, so this is the process for an adiabatic change, and you can also represent it in terms of temperature and volume and pressure and temperature. For example, in terms of temperature and volume, this would be tv to the power gamma minus 1 would be constant, and in terms of pressure and temperature, using ideal gas equation, obviously we are writing all these proportionalities. So p to the power 1 minus 1 into t to the power gamma would be a constant. So this is how several state functions will be related for an adiabatic change. And let's now look at the work done by the gas, okay, for an adiabatic process. So delta w, the relationship which we are having is nothing but p dv from initial to final, and let's say pv is equal to constant we are writing. So in place of c p, let's write it as c v to the power minus gamma dv, and from some initial to final state. Okay, and when you will be integrating this, what you will be getting is over here c into v to the power minus gamma plus 1 upon gamma plus 1 over here from some initial to final state. Sorry, in denominator we are having minus gamma plus 1. Okay, so here when we will be substituting that, you should realize that cv to the power minus gamma into v we can write, and cv to the power minus gamma is nothing but p. So the numerator become, let's say, p into v upon minus gamma plus 1. Okay, from initial to final, and you should realize that would be nothing but say p1 v1 minus p2 v2 upon gamma minus 1, you can write. And this alternatively could also be written as minus nr delta t upon gamma minus 1. So this expression here is work done by the gas for a for an adiabatic process over here. So that is work done by the gas. Obviously, delta U, this expression for delta U is going to be remain same for every type of process, and that would be nothing but NR delta, sorry, NCV delta T or NR T upon gamma minus 1 you can write. So obviously, you can also realize that delta W plus delta U is going to be equal to 0. So delta Q is equal to 0 also. You could have simply got it by integrating dq, because dq is equal to 0. So integral of dq, that is delta Q, that will be 0 as well. And you should also realize that the molar specific heat capacity for a adiabatic process, okay, you should realize that is defined by dq upon n dt, and this dq term is equal to 0. So this would be nothing but equal to 0. Okay. So the idea here is you do not need to supply any heat in order to change the temperature of the gas, okay, for an adiabatic process. It will be coming at the cost of work done by the gas itself. Okay. And one more thing I want to notice here is the difference between isothermal and adiabatic curves. Difference between isothermal and adiabatic curves, because both of these curves are going to look very similar. Okay, one is PV to PV is equal to constant, and another is PV to the power gamma is equal to constant. So let's say on PV plot we have been given two curves, let's say like this. Let's say this is curve number 1 and this is curve number 2, and we don't know which one. Like, we first of all, we know that one of it is adiabatic and the another one is isothermal, but we don't know which one is which. Okay, so how are we going to find out that? So we will be able to do that, you must understand, from the slope of the curve. So dp by dv, and let's take its absolute value, because dp by dv was a negative quantity for both isothermal and adiabatic. So for isothermal process, we have learnt it already that it would be minus p by v. So its absolute value will be simply p by v, and dp by dv for adiabatic process we learned, okay, is going to be gamma p by v over here, and gamma is a quantity which is greater than 1, because cp is greater than cv always. Okay, so you should realize that the slope of adiabatic curve will be greater than that of slope of, or the magnitude of slope of isothermal curve at a given pressure and volume. So let's say this is the point which we are looking at. So at this point you can see that the magnitude of slope of curve 1 is greater than that of 2. So it is clear that one having more magnitude of slope, that would be adiabatic one, that is adiabatic. Okay, and the 2 is obviously isothermal. Okay, so that is how you can compare. Okay, and being said that, like, since we have learned about an adiabatic process, let's take one very simple example. Okay, let's say P versus P graph of a thermodynamic change is given to us, and this looks like, let's say this is some P naught and V naught, and let's say this is some guideline over here, and some process, let's say this is some initial state 1, and along this straight line we are moving to some final thermodynamic state, equilibrium state 2. Okay, so we here, like, this is the thermodynamic process, and the question is that if 1 mole of an ideal monoatomic gas undergoes a linear reversible process A to B, or 1 to 2 you can say, what will be the volume of gas when the process turns from endothermic to exothermic? From endothermic to exothermic, so that you have to find out what would be the volume at that point. Okay, so here, first of all, you should realize how the temperature is changing. You should realize, okay, like, for example, these would be, for example, isothermal curves. Okay, something like these would be isothermal curves. Let's say this is T1, this is T2, this is T3. And I told you already that in these isothermal curves, so T3 is greater than T2 is greater than T1. So you should realize, so as we are moving from this point to this point, the temperature is changing from T1 to T2, then T3, and then back to T2, and etc. like that. So clearly you can see first temperature is increasing, then temperature is decreasing. So basically, to a certain stage, the process would be uh, uh, you can say process would be endothermic, and then it will become exothermic. So we are interested at the point where at which point exactly, at what volume it will become endothermic to exothermic. So we are basically looking for a point where dq will be equal to 0. Obviously, before that dq is negative, and after that, sorry, dq is positive, and after that dq is negative. Okay, so we are looking for the point where dq will become 0. So the point where dq will become 0, the slope of this line would be tangent to an adiabatic curve. So this here is, let's say, an adiabatic curve. Okay, so tangent of this line, or the slope of this line, will be a tangent to this adiabatic curve at that point. So that's the idea. So at this point over here, you should say that dq is equal to 0. That is, line AB will be tangent to adiabatic curve. Okay, so let's compare the slopes of adiabatic curve at this point and the slope of this line. So you should realize, for adiabatic curve, the slope is nothing but minus gamma p by v, and the slope of this line, you should realize, is nothing but simply minus p naught upon v naught. Okay, and this minus minus you can cancel, and this would be the corresponding equation. Obviously, using the equation of this line, we will be able to express p in terms of volume, and this will be giving us the required volume. So let's try to solve. So that would be gamma upon v, and p can be written as p naught minus p naught by v naught into v, and that would be equal to p naught upon v naught. Okay, and this will be simply giving you gamma upon v will be equal to gamma plus 1 upon v naught, and solving, like further simplifying, you will be getting v is equal to gamma v naught upon gamma plus 1. And in the question, it has been given to us that the gas is ideal monoatomic. So gamma, the value of gamma for a monoatomic gas, we know that is 5 by 3. So that would be 5 by 3 v naught plus 8 by 3 v naught. So our answer here would be nothing but 5 v naught by 8. So that is one of the very famous question. Okay, the next thing we are going to look into another type of process, which is known as polytropic process. And a polytropic process is any process like PV to the power some K is constant, and k could be anything except 0 and 1. K could be a positive quantity, a negative quantity, a fraction, whatever you wish. Only it should not be equal to 0, because in that case it will, p is equal to constant, will become isobaric process. And like for example, if k is equal to 1, pv is equal to constant, that will become isothermal process. So basically we are leaving those cases. Okay, so in that case, for thermodynamic change, okay, we are interested in finding out work done by the gas, and then we will be interested in finding out the change in internal energy, and ultimately we will be interested in finding out delta Q. Okay, so delta W, first of all, that would be nothing but integral of P dV from some initial state to final state, and its calculation will be very similar to that of adiabatic process. Only difference is, in place of k, we have, in place of gamma, we now have k. So let's skip those steps, okay, and simply write the final equation, and that would be nothing but P1 V1 minus P2 V2, and only in place of gamma we will be having K, so that would be upon K minus 1, or alternatively you can also write it minus NR delta T upon K minus 1 over here. And delta U, like always, independent of process, like it is always going to be NR delta T upon gamma minus 1, that is nothing but NCV delta T. So delta Q here, that would be according to the first law of thermodynamics, that would be delta U plus delta W over here, and that is going to be this quantity plus this quantity. So obviously NR delta T you can take common, and that would be 1 upon gamma minus 1 minus 1 upon K minus 1. And you should realize, for example, if you wish to find out the molar specific heat capacity of this gas, okay, so delta Q would be nothing but NC delta T, also you can write for polytropic process. So C polytropic, you should realize, that is nothing but this quantity over here, R into 1 upon gamma minus 1 minus 1 upon K minus 1, and that is one of the very important relationship. Please do remember this. Okay, so this is work done, change in internal energy, delta Q, and molar specific heat capacity of a gas for a polytropic process. Okay, and now let's take one very simple question of a polytropic process. So let's say we have a gas chamber, and we have fitted a frictionless piston inside this gas chamber. Okay, and this piston is connected with a spring of spring constant K, and this side of the chamber has some gas, and the another part of this chamber is nothing, that is vacuum. Okay, and what we are doing over here is we have put a heater in this part of chamber which would be supplying some heat, that is a heater. Okay, so obviously when the heater will supply heat to the gas will try to expand, the pressure will increase, that increased pressure will push this frictionless piston in forward direction, compressing the spring, you should realize. And in this question it is given to us that natural length of the spring is equal to the length of the vessel. Okay, so like for example, if this distance is x, so then the compression in the spring is x as well. So now the question is, for 30 joules of heat supplied, okay, by this heater, okay, change in internal energy, change in internal energy, or delta U simply, is 25 joules, or increase in internal energy is 25 joules. Okay, so from this given data we have to find number of atoms in the molecule of gas, in the molecule of gas. So basically, we have to find out the atomicity of the molecule, whether it is a monoatomic and polyatomic or diatomic. So we could find out using, like, if we are somehow able to find out the value of gamma, okay, we will be able to do that because we know for what value of gamma which type of gas is there. Okay, so how do we approach this problem? So this problem is a very unique example of a polytropic process. So you should understand, let's say at any instant the pressure is P over here, the gas pressure is P, and let's say the area of the piston is A. Okay, so at this instant when it is moved slowly, so P times A would be the force exerted by the gas, and since at this stage the spring is compressed by X, so spring would be exerting Kx force in this direction, and you should realize that PA is nothing but equal to K into X. And also you should realize what is the volume of gas right now. So V is nothing but cross-sectional area into X over here. So X is nothing but V upon A. Okay, so P times A is equal to K times X, and X is nothing but V upon A. So looking at that, all these K, A, etc. terms are constant. We can simply see that PV to the power minus 1 is basically a constant, and this here is example of a polytropic process having K is equal to minus 1. Okay, so now for this, what things that has been given to us is that is heat supplied and internal energy. So we can very well find out like delta W by delta U. So delta W here would be nothing but you should realize delta Q minus delta U. So that is going to be 5 joules. Okay, and delta U over here is going to be you can say 25 joules that is given to us. And the expression for delta W for a polytropic process we have just got, that is nothing but minus nr delta T upon K minus 1. Okay, and that divided by change in internal energy is going to be nr delta T upon gamma minus 1, that will be equal to that we have already got, that is 1 by 5. Okay, so solving this, the value of K we already know. So gamma minus 1, we will be nr delta T obviously will get cancelled. So gamma minus 1, we will get it as 2 by 5. So gamma here is 7 by 5. So 7 by 5 is the gamma. That clearly says that we are having diatomic gas. Okay, so the number of molecules of the gas is simply equal to 2 over here. Number of atoms in the molecule is 2 over here. So that is one thing. Okay, another next thing we want to discuss is about cyclic process. Okay, so let's discuss about cyclic process. And as the name suggests, cyclic process, okay, is a process where initial and final thermodynamic state would be same. Okay, like for example in P versus V plot. Okay, if we represent it, so let's say it would be some forming some cycle. Let's say this is initial state and we have some thermodynamic change, but final state is still the same. Initial and final state are still same over here. So that is an example of cyclic process. And you should realize, first of all, you should realize that delta U, okay, since initial and final state are same, delta U is going to be equal to 0. Please notice, okay, for a cyclic process, du you cannot say is equal to 0, because so for a small change, okay, for a small part of this process, the temperature may change. But since like for the whole process, initial state is equal to final state, so delta U will be equal to 0. Okay, so for according to the first law of thermodynamics, you should realize, since we say that delta Q is equal to delta U plus delta W, for a cycle you should understand like this term is equal to 0 for a cycle. So for a cyclic process, delta Q cycle will also always be equal to delta W cycle over here. And also you should realize like work done by the gas over here. Let's talk about work done by gas for a cyclic process over here. So first thing you should understand that work done by the gas would be area enclosed by the cycle. Area enclosed by the cycle. Let's say for example this area over here, the justification for this you should realize, like for example this is state A, and for example let's say we are taking state B over here. So first of all, there would be work done in this process over here from A to B, so that would be this whole area. Okay, and there would be some negative work done in from B to A, so that would be this area over here. So when we will be summing up the work done, you will be left up with the area enclosed by the cycle over here. So for a cyclic process, the area enclosed by the cycle on PV graph will be simply work done by the gas. And the another thing you should realize, if cycle is clockwise, like the diagram drawn above, you can see the positive work done in process A to B is greater than the negative work done in process B to A. So the net work done is going to be positive. sorry, positive it would be. And also if cycle is anti-clockwise, that means other way round. So obviously delta W will be negative, that you should understand. Okay, and we also define thermodynamic efficiency of a cyclic process. Okay, so in physics, basically, when we deal with engine, our main motive is to extract as much work as much possible. Okay, so efficiency is basically defined as work done by the gas, work done by the heat input. Okay, so whatever heat we are adding into the system. Okay, obviously some heat would be rejected. Okay, so like our cost is only heat input, and our benefit is work done. So that is how it is defined as work done upon heat input. So that is basically W upon Q in, you should realize. And from the above equation which we have learned, delta Q cycle is equal to delta W cycle. So delta W cycle, you must realize, delta Q cycle can be written as Q, some heat we are adding and some heat we are losing from the system. Okay, so this can be written as like this. So delta W, that would be in numerator, that would be Q in minus Q out. Over here obviously we are taking the absolute values because we have already taken this negative sign over here. So that is Q in. So that would be simply 1 minus Q out upon Q in over here. So that is basically the thermodynamic efficiency of a cyclic process. Okay, so let's try to find out the thermodynamic efficiency of a Carnot cycle. Let's find out efficiency of a Carnot cycle. So let me discuss the PV curve of a Carnot cycle, and it looks something like this. Let me tell you. So say from state 1 to state 2, and state 2 to state 3, and from state 3 to state 4, and back to state 1 over here. So what are these processes? From 1 to 2, you realize that is nothing but isothermal expansion. So say from 1 to 2 temperature is constant, and that is, let's say, TH, and from 2 to 3 that would be adiabatic process. So let's write adiabatic expansion. Expansion means we are increasing the volume, and from 3 to 4 you should realize that is again isothermal process. So like 3 to 4, let's say temperature is constant, and that is equal to Tc, so that we will know it as isothermal. And since the volume is decreasing, so that would be a compression. Okay, and back to 4 to 1, 4 to 1 is again adiabatic process, so that is adiabatic compression, let's say. Okay, so a Carnot cycle is comprised of these four processes. Okay, either the processes are isothermal or adiabatic, you should realize. So you should understand adiabatic process, there would be no heat exchange between the system and surrounding. So you should realize like heat exchange between the system and surrounding would be like, for example, 1 to 2. Okay, since that this is expansion, so heat will be basically added to the system. Let's say that would be Q in, and from 3 to 4 heat would be released by the system. Let's say that would be nothing but Q out over here. So that is the idea. And in process 2 to 3 and 4 to 1, because the process is simply adiabatic, there would be no heat exchange. So in order to find out the efficiency, like we defined, eta is defined as 1 minus Q out upon Qn, we simply need to find out this quantity over here. So first of all, let's try to find out how much would be Qn. What would be Qn? So Qn, you should realize, is an isothermal process. 1 to 2 or 3 to 4 is an isothermal process. In isothermal process, delta U is equal to 0 and delta Q is equal to delta W only. Okay, so the formula which we will be using is nRT ln V2 by V1. Okay, so nr temperature is Th, obviously from 1 to 2 temperature is Ts, and ln final volume by initial volume, so you should write it as V2 by V1 over here, V2 by V1 over here. So that is Qn, and similarly we can find out Q out, and since we are looking at its absolute value, obviously this work done would be negative, but we are looking at its absolute value, so it would be nRTC. From 3 to 4 the temperature is constant, and that is equal to Tc, and that will be equal to nothing but ln V3 by V4. Its expression should have been final upon initial, that would have been V4 upon V3, but since we are taking the absolute value, this is the magnitude of Q in and Q out over here, so that you should realize. Okay, and also you should notice in this diagram over here, also you should notice for adiabatic process, since 2 to 3 the process is adiabatic and 4 to 1 the process is adiabatic. So let's try to relate between um, these two to 3 state and 1 to 4 state. So let's realize for adiabatic process, we know that Tv to the power gamma minus 1 is equal to constant. So if we write the equation between for this process over here, what we will be getting here is you can say V3 upon V2 to the power gamma minus 1 would be nothing but T2 upon T3, using this relationship right over here. And T2 is, you can say, the temperature at T2 is nothing but Th, and T3 is nothing but Tc. So this is, let's say, for the first equation, and that is for the pressure 2 to 3. And now let's look for this process from 4 to 1. Okay, so again that is adiabatic process, so we can write, okay, that would be V4 upon V1 to the power gamma minus 1. These two states we are comparing. Okay, so V4 upon V1 to the power gamma minus 1 would be nothing but T1 upon T4, and T1 you realize is again Th, and T4 is nothing but Tc, you should realize. So that is equation number 2, and you must understand that the right hand side is same, so that gives us the left hand side will also be same. So simply V3 by V2 would be nothing but V4 by V1 over here, and also you can write it as like V2 by V1 is equal to V3 by V4 over here. So this relationship gives, like for example, this quantity and this quantity would be exactly same. So when you will be taking the ratio, this ratio over here, okay, this term will get cancelled, and nr obviously will get cancelled as well. So eta you will be getting it as 1 minus Tc by Th over here. So that is the efficiency of a Carnot cycle. Let me also tell you a little bit about the second law of thermodynamics. So it is not possible to design any cycle whose efficiency is greater than that of a Carnot cycle. Okay, so if an engine would be operating via Carnot cycle, its efficiency would be maximum. So being said that, let's also talk a little bit about heat engines. Heat engines. Okay, so heat engine, let's say there is a block diagram. So let's say this is a heat engine. Okay, so it operates between a hot reservoir, you can say hot reservoir, okay, and cold reservoir. Reservoir is something which reserve heat, Okay, and if you extract some amount of heat, okay, the temperature of it will not be changing significantly. So let's say temperature of heat reservoir is constant at TH and temperature of cold reservoir is constant at TC. So heat engine is something which extract heat from a hot reservoir, let's say Q1, and releases heat to cold reservoir, let's say Q2. Okay, and tries to convert this heat into work. So that is, say, W. So obviously, this would be a cyclic process. It would be operating in a cycle. So delta U is equal to 0. So delta W is equal to Q in minus Q out. So that would be simply Q1 minus Q2 over here. And efficiency, its efficiency we will be again be defining same way we define the efficiency of a cycle. So that would be nothing but work done by heat input, which is nothing but Q1 over here. So that's going to be Q1 minus Q2 upon Q1, and that is going to be 1 minus Q2 by Q1. And if this engine operates via a Carnot cycle, the maximum efficiency that would be maximum, and that will be for a Carnot cycle, and that would be nothing but 1 minus Tc by Th. That is nothing for a Carnot cycle. And let's also very quickly discuss about heat pump or refrigerator. Heat pump or refrigerator. Okay, so the unit of heat pump or refrigerator is basically it also operates between hot reservoir and cold reservoir. So let's say temperature of hot reservoir is constant at TH and temperature of cold reservoir is constant at TC. And difference between the heat pump or refrigerator and the heat engine, okay, the only difference is like this unit will be extracting heat at lower temperature. So let's say this would be Q2, and it will release heat at higher temperature, and that would be Q1. So obviously, in order to make it happen, we need to provide it some energy, we need to provide it some power, we need to do some work on that system. So work is being externally done on it. Okay, so whereas engine is a device which you require to do work, wherever when you want to operate a heat pump or refrigerator, you need some external power source. You must realize without electricity, either heat pump of or refrigerator is not going to operate. So we need some external power source, and this W, you should realize, will nothing but like the balance between Q1 and Q2. So that is Q1 minus Q2 over here. Okay, so here our, like for example, depending upon whether it is a heat pump or whether it is a refrigerator, we are interested in either Q1 or Q2. Okay, now you realize for heat pump, as the name suggests, okay, this would be needed to heat some like for example, heat some cold region. Okay, heat some cold like for example, we are having a room and we want to heat it, and surrounding is cold. So from the surrounding we will try to take heat and deliver it to our room. So basically, for heat pump, how much heat is delivered to the cold reservoir, that is we are interested in. So coefficient of performance, basically coefficient of performance for a heat pump, we define it as nothing but Q1 upon the work done, that is Q1 minus Q2 over here. So that is the idea. Obviously you for a Carnot cycle, you understand that Q2 by Q1 is TC by TH, etc. And also you should realize for a refrigerator, and you all have experience to work with refrigerator. I think my pen got hanged. You all have experience to work with refrigerator, and you should realize that refrigerator is a unit, okay, which tries to keep a space cool. Okay, so basically you can say the refrigerator unit. You take some heat from it and release heat to the surrounding. So in refrigeration unit, it is important for us to keep track of this, that how much heat is uh, taken from the cold reservoir. So coefficient of performance of a refrigerator is defined as Q2 upon Q1 minus Q2. So please mind these two differences between heat pump and a refrigerator, although their working principle is same. That is, both of these extract heat from a cold reservoir and deliver heat to a hot reservoir, and work has to be done on that unit. Okay, but their coefficient of performance are defined differently. And now we are running out of time. Okay, so that's it for